Okay, question 4. Figure 6 shows 4 forces, P, Q, R, and S, acting on a rod. The rod can rotate around the axle. So here is the pivot. And the crucial thing then is we're looking for turning moments. So if I put a force on the pivot, they're going to be pointless. The next part is if I push it along the axle, that's not going to work. There we go. That will give me a turning moment. So the answer is B, letter Q. On to the next one. Figure 7 shows a person trying to lift up a big rock using the bar. Tells me here's the pivot, and we've learnt the principle of moments. That is the, what we've got this side, the anti-clockwise moment will equal the clockwise moment if it's balanced or if it's in equilibrium. Oh God, spelling. If it's in equilibrium. So that's the principle of moments. The anti-clockwise moment will equal the clockwise moment. Now, the next part now is, well, if I want to lift this rock, this moment has got to be bigger than that moment. Okay, so we're going to now check that. And how I taught you in class is shove a line down the middle from the pivot. Here's the anti-clockwise on that side, and the clockwise is on the other. We want to make sure the anti-clockwise is greater than the clockwise. So the force of the person must be greater than that rock so they can lift it. Do a bit of maths. So we've got fat, moody dinosaurs. And this is the perpendicular distance from the pivot, which they give you there. Remember, they might always try and catch you out by putting that one there. We don't ever want that. We want the perpendicular distance. So 90 degrees to the pivot. So now just do some little multiplications. So the turning moment for the anti-clockwise, 600 times 0.5. Using those numbers up top there, directly above. That equals 300 Newton meters. Perfect. We're now going to see, is that more or less than the rock? So 1,800 times 0.2, 360 Newton meters. The person is less than the rock. No. All right, so they cannot lift the rock. Why? Because the anti-clockwise moment is less than the clockwise moment. And it's all of this thing of talk about the clockwise and the anti-clockwise and always blinking label it. Because it's a nice, easy question, this. But you've got to state, here is the anti-clockwise. There is the clockwise with that rock. Okie dokie. Explain one change to the arrangement that will make it possible for the person to lift. Well, we've just said we know turning moments of fat, moody dinosaurs. So the two things I can change is increase the distance from the pivot or increase the force. Ba-dum. So increase the distance, the person's force from the pivot, 1 mark. Increase the person's force, but it says explain one change. So that is not 2 marks. So the next thing we've got to add is, and we just explain why that is, and that's because we'll increase the turning moment as that equals the force times the distance. And I'll go with this one. So if that goes up, this goes up. Da, 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 da. Put that into a sentence. That's the basic idea. But it's not 2 marks for things. Explain one change. So I've got to link it to and the turning moment equals force times distance. So if distance increases, then turning moment increases. Next one. Now we've got a bike. Now we've got a small gear over here. Tiny weeny one. Big juicy gear over there. And it says the rider uses the pedals to make the large gear turn. The large gear is 48. The small gear is 12. The large gear turns 2 times each second. So we know that this turning next to a small gear, this is going to have a higher period of rotation. All right, so we're pretty happy with that. So calculate the number of times that the small gear will turn. So it's find your gear ratio. So 48 to 12 simplifies to 4 to 1. Now I've got my unitary number 4. Well, I know the small one's going to rotate more often, so I just need to times by 4. So 2 times 4 equals 8. It's going to turn 8 times per second. And always just get into that idea of going from a big to a small. The rotations go up and the torque goes down. Oil is applied to the bicycle. Perfect. Explain how this improves the efficiency. So my marks here are talk about friction, talk about oil as a lubricant and will remove friction, and therefore there's going to be less wasted energy as heat. Here we go. So oil reduces the friction, Less energy will be lost as thermal energy, so there's more useful kinetic energy because efficiency equals useful over total. So use your formulas in your booklet all the time. Just shove them in. They're written for you at the back. And there we go. That's that question done.